last lecture. Just a few reminders. We are going to have the group photo right after this lecture. So we'll meet outside, and if it's still not raining, we'll go outside and take the photo. The contest on high ranks, you have to send me your entries by 11:59 tonight. And remember the rules. You have to send me a coordinate. You have to at least send me points to verify that the rank is what you claim it is. There is breakfast outside tomorrow, like every day, but there are no other lectures except that we plan to have from 10:30 to 11:30. Some of the organizers will be here. And it will be a Q&A session. If you have questions about material, we can answer that. If you have questions about, I don't know, life, grad school, going to grad school, going into writing thesis in these kind of areas, anything you want to ask, that's a free format. Okay, so we'll be here and you can come, but this is not mandatory, like none was mandatory, so it's up to you if you want to rest in the morning or come and hang out over here. Okay? All right. So, with all that said, we were trying to do a descent, okay, on elliptic curve. And the method of descent, remember that there are these homogeneous spaces that with maps down to the elliptic curve. And if I have a point on the elliptic curve, it lives in one of those homogeneous spaces. There's a map over there. And if I find the points in these homogeneous spaces, I can send them back to points on the elliptic curve. And the beauty of it is that these maps going from here to here are height increasing, meaning the height of the point that we talked about, they're height increasing. So going in that direction, they're height decreasing. So it's easier to find points here than finding points here because the coefficients are smaller. You can see it in the map that I'm squaring the x-coordinate. Okay, so that's why it's in the height, which is through logarithmic, the height doubles going this direction in broadly speaking. Okay? All right. So let's try to do, I'm going to do one toy example here. There are a couple of other examples in the chapter 2, at the end of chapter 2 in the notes that have more meat to them. But this is all I can do with the time I'm given. That I'm giving myself, I guess. Blame the organizer. Okay, so that elliptic curve, this is my E. And in this, remember we defined this map and we said this is an injected homomorphism, and I'm going to try to do that to calculate what the rank is. All right, so here my E1 is going to be 0, my E2 is going to be 1, my E3 is going to be -1. What is the delta here? The delta is E1 minus E2, E1 minus E3, E2 minus E3, and that turns out to be -2. Then the primes that can divide that quantity is just the prime 2 and the prime infinity, meaning that I can put minus signs. Okay, so the place infinity. So this gamma set are pairs, delta 1, delta 2, with the deltas in ±1, ±2. Okay, so there are 16 of those possibilities, and the homogeneous spaces that appear here with, I don't have the formula for the homogeneous space for you on the board, I don't think. So the homogeneous space, C delta 1, delta 2, in general is of the form, we reduced it to this form. You can reduce it in several ways. We're going to use it like this. Okay, so in this case, E3 minus E1 is minus 1, is delta 1 x squared minus delta 1 delta 2 z squared, and E3 minus E2 is minus 1 minus 2 delta 1 delta 2 y squared minus delta 1 delta 2 z squared. Okay. So what I want to do is look at all the spaces. There are 16 of them, and I want to find all the points that are there, see what I get. Okay? So what I'm going to do is a table to make sure I don't miss anyone. Okay, so here is, I'm going to put 1 and 2 and minus 1 and minus 2, and 1 and 2 and minus 1 and minus 2. And look at all of them. See which ones have points, which ones don't. Okay. The 1, 1, this is a homomorphism. Should the 1, 1 have points? What's my trivial element in this group? So this is a group with respect to multiplication. 1, 1 is identity. I have an identity here that has to go to the identity. So that element always has a rational point. Let's see if that's true. With 1, 1, I get x squared minus z squared. So I can pick x0 and z to be 1. And I get y squared minus z squared. And then I can pick let me not get stuck in that point. O goes to the identity element there. 1, 1. Let's see what the solution is in y, z. 1. O goes to that space. Maybe I'm missing some denominators or something. So let's let it be. O goes there. So what about the other points? The easier way to rule out some of these spaces is for now. Well, there are squares in places, so maybe I can use that to rule some of them just by signs, right? For instance, this has to be negative. So if this is positive, then that cannot be a negative number. So what happens if delta 1 is positive, but delta 2 is negative, then this is a square plus a square equals a negative number, and there cannot be solutions. Okay? So when delta 1 is positive, but delta 2 is negative, those are impossible. Okay? So I'm going to mark that as, I'm going to write what the problem is. Okay? So I'm going to say that over the reals there are no solutions, and I'm going to put an R there to mark that. So I'm going to write here as remark. That if delta 1 is negative and delta 1 is positive and delta 2 is negative, then no solutions over R in my homogeneous space. Okay? So those are gone. Are there other ones that I can roll out like that? Now, reverse the role of delta 1 and delta 2. If delta 2 is positive and delta 1 is negative now, this doesn't have solutions over the real numbers, okay? So this had a problem with the first equation, that minus 1 would be delta 1 x squared minus delta 1 delta 2 z squared. This would be positive. And if delta 2 is positive, delta 1 is negative, then no real solutions in here in the second equation. Okay? So I can cross these out, and again I do that blaming the reals. Okay? Very good. Now, something I didn't say last time, and that unfortunately I just erased. Can you see it here in like white? I worked very hard, so you can kind of see it there. That the torsion points, you see that. Remember how the map was defined? Here, I'll mark it again. P goes to xp minus e1, xp minus e2, and you take the square free part of those numbers. That was my map from points to pairs of deltas. But obviously that doesn't work. If the x-coordinate is e1, I get a problem because that's 0, and then there's no square free part there. And if x is e2, I get a problem too. So the torsion points at O, in fact, the map is defined differently. So O goes to 1, 1. E1, comma O goes to E1 minus E2 times E1 minus E3, comma E1 minus E2. E2, comma 0 maps to here, E2 minus E1, comma E2 minus E1, E2 minus E3, and E3, comma 0, this guy maps to E3 minus E1, comma E3 minus E1, E3 minus E2. Okay, so in my particular example, O goes to 1. I've already marked that. E1, comma 0 is going to go to, E1 is my 0, so it's E1 minus 1 times E1, 0 minus minus 1, so this is minus 1, comma, E1 minus 2, again it's minus 1. So it goes to minus 1, minus 1. Okay? So there is a rational point, but I know that that corresponds to one of the two torsion points on my elliptic curve. So minus 1 is okay, but it comes from something I already know, which is 0, 0. Okay? How about, so that is my 0, 0. How about 1, comma 0? That I'm going to just tell you, it goes to 1, comma 2, and minus 1, comma 0 goes to minus 1, minus 2. You can write it. You can check it. So I get 1, 0 goes here, great, and minus 1, 0 goes here, great. Okay. Now you can start checking these things. So if you remember how we defined this map, that was fine. It didn't seem like it wasn't very special of a definition. I just took the square free parts and just made sure that the square free parts multiply to be a square, and that's how I define the spaces. What is surprising is that the map that I get is a homomorphism of groups. Okay? So now you start to see the surprise that, well, I know that this is P and Q, then P plus Q equals T in the two torsion group. Okay? So it should be also the case that if I go here and I do P plus Q, and now I'm talking deltas, I should get the third one. So what I'm saying is, note that the group law holds that -1 minus 1, if I multiply by this guy, which is 1, 2, I get -1 minus 2, which is this guy here. Okay? And that corresponds to the addition on elliptic curves, that if I add 0, 0, and 1, 0, I get this -1, 0. That is the part that is surprising about this map, okay? That holds. And we're going to exploit that. Okay, so now I have 4 holes, and so there's still some room that I could have a point of infinite order that fits here. And then using the, I cannot get any more than that, because once I have 1, multiplying by the other torsion points, I'm going to fill out all the other boxes. Okay? So I have to check that there's some space that has or doesn't have more points. So let's see the 1, 2. So what about 1, 2? The space C12 is -1 equals x squared minus 2z. No, it's 2, 1. So it is 2x squared minus 2z squared, and minus 2 equals delta 2 is 1, so it's y squared minus 2z squared. Are there rational points? Anything like it? Are there integral points? Can the x, the y, the z be integers? You are shaking your head vigorously. What?
The right side is y2.
Yeah, so at the very least, they are not integers because, well, this is even, that's odd. So there are no integers. So I'm going to leave it as an exercise. Ask me if you get stuck, but that idea will carry over. If you throw in some denominators, you just have to worry about, it will be a question of even or odd, right? So if you throw some denominators, you can show that these equations cannot have solutions over the rational numbers either, okay? But you see, as I say, the only thing you have to worry about is the powers of 2 in the denominator and the numerator. The argument is about evenness. So what that means is that what is actually failing here is Q2, is the 2 at x. You can actually show that there are no Q2 solutions. Okay, the 2 at x are bigger than the rational number, so it's something stronger. But the argument, see, if the argument is just about divisibility by 2, it will actually extend to proving that there are no 2 at x solutions. So I'm going to blame Q2 here for it. Okay, there are no points over Q2. And now, as I said, now I'm going to use the fact that this is a homomorphism. Is there a point here? Well, if there was a point here, I'm going to be able to multiply, this is 2, 2. If I multiply by 1, 2, what did I get? How much is 2, 2 times 1, 2? That is 2, 2 times 1, 2. That's 2, comma, 2 times 2 is 4. I get 2, 1. right? That is this one. So if this has a point and this has a point, then I could multiply and get a point here. But there is no point here, so there shouldn't be a point here either. And that is all a homomorphism argument. Okay? So I'm going to blame Q2 here, but I'm going to do it like this guy is forcing this to be Q2 by multiplying by, we'll probably mark it, by the torsion point 1, 0 or the element 1, 2. If you multiply 2, 1 by 1, 2, you get 2, 2, and you go there. So maybe it's better to multiply by deltas, blame the delta. By 1, 2, you go there. What about this guy? If I multiply by this guy by -1, -1, I go from 2, 1 to -2, -1. I go here. So I can go here and say, no, there's not going to be Q2 points if I multiply by -1, -1. And if I multiply by -1, -2, I go here, and there are no Q2 points multiplying by -1, -2. Okay? And I filled out my chart of homogeneous spaces. We know that if there is a point on the elliptic curve, it lands in one of the homogeneous spaces. And this is all there is. So what this tells me the math tells me delta tells me that EQ modulo 2EQ injects into this gamma, and what I've shown is that the image is 1, 1, who survived 1, 2, -1, -1, and -1, -2. And that's it. Okay? Which are the points that correspond to torsion points. Okay? So this corresponds to O, this corresponded to 0, 0, this corresponded to -1, -1 is 0, 0. This corresponded to 1, 0. That one is -1, O. So this is just generated by two torsion points, and we knew they survived in that quotient, and that's it. So that tells me that EQ is actually just equal to its torsion subgroup. If you see, so you have to, there is no point of infinite order, those would show up in that quotient. However, points of finite order, that is, points of finite order that are of prime order other than 2 would be killed in here. So those would never show. So you have to make sure you calculate what the torsion subgroup is. And in this case, it is just the 2 torsion. And that's it. It is finite, and there's only those 4 elements in the Mordell-Weil group. Okay? So we've succeeded. We've done a full descent. We checked all the homogeneous spaces and found out there are no points of indefinite order, and I've completely succeeded in calculating the full Mordell-Weil group. Okay? This is, yes?
For the trivial homogeneous space, the one you were stuck on, the points are at infinity. So you're working in an affine model, but if you projectivize, so you make a W squared, and then you can take then the delta 1, all of them lie at infinity. So you take W equals 0, and then you take the 1, and that's where you find the points.
Yeah, so you can put, for instance, if you think about it in the rational numbers, also the denominators, the denominator would be sort of like what John is saying, the projectivization would give you also that. So if you put another variable here, W squared, 2W squared, then you can find the solution there. Okay. All right. So that was great. This is a deceiving example. So let's talk about what could have gone wrong. What could have gone wrong is that I got lucky that a space like this one, I was able to show that there is no solutions over a p-adic field. Okay? I was able to show that. But what if this space had solutions over the reals, solutions over every p-adic field, but there was no rational solution? The problem is, does the local to global principle hold? Can I do that as I did in quadratic equations in conics? That works by the Hasse-Minkowski theorem, but here it doesn't work. So you have to worry about spaces that are these blocks that are empty in the tables of the descent, whether I can prove that there are no points. So here I did, you see this as all local arguments. Either I found rational points or I found local fields, QPs or completions of the rationals where there are no points. Okay? So this worked out because for this elliptic curve, for this one, the local to global principle holds. Okay? Either it's locally solvable and then it is globally solvable, or it is not locally solvable and therefore there are no points. So what can happen in general then is the following. So in general, remember we have this picture. I had E, we're actually working with E modulo 2, and then I have some spaces okay, and there are maps. And if there is a point, I know that it lands in one of them, right? So the homogeneous spaces can come in three flavors. They can come in the kind that are locally solvable and globally solvable. That's the kind that hosts the rational points of the elliptic curve. Then you could have spaces that are not locally solvable. And if there are no solutions locally, like over the reals or Q2, there are no solutions over the rationals. So there are no Q points either. And then there are the problematic ones. The ones that can be locally solvable, but no Q points. And those are the tough ones. What we want is a measure of how many of these there are for any given elliptic curve. That will measure the failure for any given elliptic curve of the local to global principle. That's what's called SHA. Okay? So the first step in doing the descent of a difficult elliptic curve, like with large coefficients, is identify these spaces, the ones that are locally solvable. Okay? So those will actually be a subset. So we have all of them. This has all the spaces. But then within those is those that we call the Selmer elements. And these are going to be the deltas such that the corresponding homogeneous space is locally solvable over R and E and every QP. Okay, so that's the first start. That's easy to do. You can easily check what spaces are locally solvable. Those are not locally solvable, I can throw in the trash. Those are not going to work. There are not going to be points there. So now I have to figure out which ones of these have points and which ones don't. Okay. This is, as I said, this is the Selmer. In this case, it's a 2-Selmer subgroup, or 2-Selmer group. And as I said, we want to measure the badness of this. Since this is a subgroup of this, that's the subgroup of the Selmer group that I'm interested in, I can do the quotient. If you've seen number fields, when you're trying to figure out, is my ring of integers of my number field, is z adjoint I, is it a PID? What I can do is look at, well, give me all the principal ideals. I'm going to mod out by the, give me all the ideals, mod out by the principal ideals, and that will give me a size of how many ideals are non-principal. Okay, so I'm going to do the same thing here, and I'm going to take the 2-Selmer and mod out by those, the image of this, okay? So I'm just going to call it, again, E mod 2. So the quotient of those two things will give me the measure of the failure of the Hasse principle, the Minkowski-Hasse principle. So this is called SHA, usually written with the rational letter SHA, after SHA for Revich. I'm going to put a little 2 there, but what I'm actually getting is SHA itself is a group. It's a SHA for every prime, and what I get here is actually is the 2 torsion of that group. So I'm going to put a 2 back there instead to reflect that. Okay, so I'm just getting a tiny piece of that, and this is it measures the local to global failure. And those are the big problem here. I don't know how to identify those with local methods fail, so how do you identify those? What you do is when you find one of these, what happens is that, okay, it's locally solvable. I'm going to let my computer run for a while. And I don't find points. I start to get suspicious and worried that this is a SHA element. So what you do is a farther descent. I'm going to take this now as my original curve, and I'm going to find farther homogeneous spaces. This is called a 2 descent. That would be the beginning of a 4 descent.